my x value. And so when we find average rate of change, what we do is we just divide that net change and average it over those 3 units that we changed to x. So it's like, oops. It's like making little steps, right, that are all the same size. So every time we move to the right 1 unit on the x-axis, then my y value is changing on average 2 units. Notice that it's not actually changing by 2 units for each of those intervals, right? Like the tops of my steps don't match up with points on my function, and that's why we call it the average rate of change, because we're not actually saying that this is the change in the function, like from here to here and from here to here and here to here. We're saying, okay, this is the change over 3 units, and I'm just averaging it over all 3. So when we calculate average rate of change in a function f between x equals a and x equals b is given by average rate of change. You can abbreviate if you want, because it is a lot to write. So, well, what did we do here? We took the net change, right? So net change in f and then divide that by the change in x. So symbolically, net change is f of b minus f of a, exactly like it was last week. And then my change in x I'm going to get just by subtracting my x values. A few things. So there's kind of, with this average rate of change stuff, there's kind of a lot that you have to say in order for it to be accurate. First, we need to say what the x values were that we used, because the average rate of change isn't the same between different points, right? So just like net change, it depends on where you are on the graph. And so we'll say between (2005) and 2009. Of course, you want to make those into years rather than saying like between 5 and 9, right? Because once we've taken that out of the function that told us it was years since 2005 and 9 could mean anything, right? So then you want to say what's changing. So in this case, the median home price and then you always need to give direction. So this was one thing that you might have noticed on your homework when you did that interpretation problem of net change, is like, I said, like, what direction did it change? If you say something like between 24 jars and 12 jars, the cost changes by $109. Did it go up or down between 24 and 12? The cost, that is. If it's a positive change, then the cost went up, right? Which isn't true, right? Between buying 24 jars and buying 12 jars, the cost did not go up $109. So you have to be kind of careful about direction of things. If you say between here and here, I'm imagining you're going from beginning to end, right? And then the sign on the change in your y value has to correspond to that, or the direction of that change. With time, it's pretty obvious which direction we're going in. But if your inputs aren't time, you want to be really careful about like what you started with and what you ended with. So it's always from the lower X value to the higher X value. And so in this case, when we went from 2005 to 2009, our median home price went down. So we want to say decreased. By an average. And that average is important also because it is not true that every single year the price decreased by $12.5 thousand, right? If we go back to our graph, like between 2005 and 2006, the average home price actually went up. It definitely didn't go down $12.5 thousand. So what we're saying when we do average rate of change is we're averaging the change from that point to that point. And so we have to say average, otherwise we're saying that something's happening that isn't actually happening. Of $12.5 thousand dollars. So that's our change, and then we have to say something about the fact that that's only over 1 year. So depending on the problem, like the way that you say that, I mean, in this case, per year makes a lot of sense. You could say every year or each year. But if you just say 12,000, that's saying that it changed by 12.5 thousand over 4 years. So you need that like per year to show that it's a unit change rather than like just the net change in the whole thing. So every year. So there's a lot to these sentences that we have to make sure is in there. We have to make sure that the change in X and the change in Y is in there. And that they both have units. We have to describe what the Y value represents in words and what the X value represents in words. And then there has to be a direction. So the direction of the X value is implied by you saying between this and this, right? So that's saying you're going from 2005 to 2009, but we have to say increased or decreased to give the direction of the change in the Y value. Notice we never put a negative sign in here because, I mean, nobody talks like that, right? Like, oh, the price changed by negative $12,500. So the negative sign is accounted for by the word decreased. So that always has to be there. And then we always have to have that word average to show that we're averaging that change rather than saying that it actually changed that much every year. So you just want to make sure that all of those components are in your sentences, because that's like when I grade these on tests, I'm like point, basically. And so like I look for each one of those little pieces. Okay. I'm not actually going to do this problem, but I want to say one thing. If the input of a function is time, and the output is distance, the average rate of change well, what would the units be? So like the average rate of change is the change in the output over the change in the input. So that's distance divided by time, which tells us what? Speed. So whenever we're in a situation where our output is distance and our input is time, the average rate of change is speed. So I only say that because sometimes we'll ask for the speed and what we want you to do is just do average rate of change the same way we did in the last problem. So for instance, a stone is thrown, oh, the stone is going to be thrown downward again. So just like on your homework, a stone is thrown, oops, I don't need the word is, thrown downward travels d meters in t seconds where d of t equals 4.9 t squared plus 34.3 t. So let's say this, if the stone hits the ground after 45 seconds, what was its average speed during the last 10 seconds? Of its fall. So I read a question like this on a test and I see the words average speed and I think, oh, that's average rate of change, and now I'll do it just like any other problem I'm asked for average rate of change on. So I need to know what the change in my x, so what x values to use to find change in x values, and then I'll use my function to calculate the change in my function. So what x values am I using? What's from what time to what time? So I heard a 0 and did I hear a 35 somewhere? 45? So remember, we want the last 10 seconds of the fall. So the end of that period will be 45, right? Mm-hmm. And the beginning of that period will be 35, right? 10 seconds before. So if we want the last 10 seconds, then you just count backwards from the end. So we want d of 45 minus d of 35 over 45 minus 35. Again, make sure you're writing this piece of it. So in general, before you start calculating everything. So we've expressed our average rate of change, and now we'll go ahead and calculate it. And when we do the numerator, now that we're not reading it off a graph this time, right? We actually have to calculate it. We're going to do that exactly the way we set up net change last week, right? With the brackets. So we have 4.9 times 45 squared plus 34.3 times 45 minus 4.9 times 35 squared plus 34.3 times 35. All over, we'll just call that 10. So one thing I've noticed on the homework is some of you, and I mean, if you want to do more work than you have to, that's okay. But some of you are doing and writing more than you have to as far as calculations go. So like, I care that you know how to set up the average rate of change and the proper notation, but I don't necessarily need to see like all of your order of operations when you Like you don't need to square the 45 and write everything down and then do the multiplication and write everything down, because I know you guys know order of operations at this point and that you know how to do calculations. So like if I were you, I would type 4.9 times 45 squared plus 34.3 times 45 into my calculator exactly as you wrote it, parentheses and all, and then your calculator will take care of order of operations, and then you don't have to waste your time like writing the result of every individual calculation. So it's fine with me if you just give me what's in that first bracket, what's in that second bracket, and call it a day. So I don't need to see all that. Does that make sense? I mean, if you want to write them all down, that's fine. But I'd rather use your time on like the new stuff than all the stuff that we know already. Yes?
We can just write that out and then put the answer.
Well, so not necessarily the final answer, just in case like you hit a wrong button. We should show a couple intermediate steps, but like what's inside those first bracket set of brackets? Has anybody done it? Get out them calculators. Sorry?
11,466.
So 11,466. So that's the first bracket, and then minus what's in those second brackets.
7,200.
Over 10. So Finn, I would probably write that intermediate step just in case like your finger slipped or something. So we know that you're on the right track, and then that ends up being what? So what do you get when you subtract?
4,263.
4,263. And really the only reason I'm even writing this step is so I can put my units in, right? We want to put our units in while the numerator and denominator are still separate. So this, my numerator is in meters, and my denominator is in seconds. Sorry. Stupid logo. And so we get 426.3 meters per second. Some of these problems are going to involve a bit of rounding. So on homework, if I don't tell you what to round to, I mean, just be reasonable. Usually like 1 or 2 digits makes sense. I'm not going to grade you on like what place value you decided to round to. But on my math lab, they tell you like in those instructions below the answer space, like round to the nearest hundredth or whatever. So make sure you read those, because it's really frustrating to like get it wrong because you rounded the wrong way. And then on tests, I'll always tell you just so there's no ambiguity and you don't have to wonder like, oh my God, is she gonna take points off? But here I don't know. I don't submit around at all. Good? Okay. Well, we talked about how functions don't have a constant average rate of change, right? So if I was looking at average rate of change between year 1 and year 4, I'm going to get something very different than if I look at average rate of change between year 6 and year 9, right? In particular, one's going to be positive and one's going to be negative, so they're definitely not the same. So average rate of change of a function depends entirely on which points you use to calculate it. That's like why when we do our interpreting, we have to say between here and here. However, there is one type of function that has the same average rate of change everywhere, regardless of what points you use to calculate it, and that's how we define a linear function. So a linear function is a function with constant average rate of change. So that just means that it's the same no matter what points are used to calculate it. Which kind of makes sense, right? Because like a straight line is always the same steepness. If we had right, it's the same steepness all the way across its domain. So that's exactly what it means to have a constant average rate of change, is that the function is the same steepness everywhere on the graph. And so we can write, see, linear functions can be written in the form f of x equals mx plus b. And so if we actually wrote a function for a specific linear function, we'd have a number for m and we'd have a number for b. M is the average rate of change. And for linear functions, we call that the slope. So the slope is a property of the function itself because it doesn't depend on where you are. We can't say that any other type of function has a slope because the average rate of change depends on where we are on the graph. So it's not a property of the function as a whole. It's a property of what 2 points we pick to calculate it. And so slope just means it's the same all the way across the board. So we can say as a whole, the function has a slope of whatever. And with with linear functions, we don't even have to say the word average because we're not averaging different amounts of change over a period. Like, it's always the same, right? So, I mean, if you said average, that'd be fine. But anywhere you see rate of change with respect to a linear function, it's interchangeable with the word slope. So we usually see the wording rate of change in application problems, and then like when we're just talking about like a function defined by an equation or something with no application attached to it, then we usually call it the slope. But they're the same exact thing. So you find them exactly the same way. And then B is the initial value. So it's the output corresponding to an input of 0. So on a graph, if this is my, let's do this one. If that's my line, this point right here, the point where we cross the y-axis, well, that corresponds to an x value of 0, right? Every point on the y-axis, I haven't moved to the right or left, and so my x value is 0. So this is, it's called the y-intercept. So it's just the point where the graph crosses the y-axis. And that's true like if this is a linear function or not a linear function. So we always call that the y-intercept, and it always corresponds to an x value of 0. In this case, that's going to be the point 0b. And then while we're at it, this isn't part of the equation, but most functions also have an x-intercept, so the point that it crosses the x-axis we call the x-intercept. Which is, and solve for x. So to find the y-intercept, we plug in x equals 0 and find y. To find the y-intercept, we plug in y equals 0 and find x. And like I said, that's true for any function. Like as we move forward and start talking about different types of functions, the way that we find the x and y intercept will be the same all the time. It's always just put 0 in here and 0 in here. So it's not a property of the fact that this is a linear function. A lot of people kind of like think it has to do with the fact that it's a line because it's like that y intercept is part of y equals mx plus b. But it's true of any function. When you plug 0 in for x, you always get the y intercept. How am I doing on time? Oh, good. So we can do this one real quick. The speed of sound at temperature T degrees Celsius is given by, so it turns out the speed of sound is not constant. It changes based on temperature. So sound waves travel at different frequencies based on how hot or cold it is. So the function that tells us the speed of sound at a given temperature is S of t equals, what did I say, 331 plus 0.6 t. So this is a linear function because it's written in that form y equals mx plus b or f of x equals mx plus b. The fact that like it's actually b plus mx is okay because addition can be done in any order, right? So the variable term can be first or second without changing anything. So let's write a sentence that interprets the meaning of 331 in this context. Okay, so we see 331 in our formula. Based on what I just told you back here, what can you tell me about that 331? What is it? Yeah, perfect. So it's that initial value, right? So it's going to correspond, it's the output that corresponds to an input of 0. So it sometimes helps people if they write it like as a point. And then we know that our inputs are temperatures, and our output is the speed of sound. So 331 degrees Celsius. Oh, no, sorry. Meters per second. Per second is the speed of sound at 0 degrees Celsius. So when you interpret those initial values, make sure there's a 0 in there. If you just say it's the speed of sound, like when is it the speed of sound, right? So make sure that you put that 0 in there. And then, do we have time to do? Let's interpret the meaning. We're going to do more of these tomorrow too, so I know we're going a little fast. Of 0.6 in this context. So in general, what is that 0.6? Like just in terms of the equation. Yeah, it's the slope of my line. So remember that slope is the change in my output divided by the change in my input. So that can really help with interpreting because you could put your units in. So what are the units for my outputs? meters per second. Right, there's speeds. And then my input is temperature, so degrees Celsius. So what this tells me is that for every 1 degree Celsius increase in temperature, the speed of sound, does it go up or down? It increases, right, because that's positive. By 0.6 meters per second. So writing it like the number like that, like as a fraction, and then assigning those inputs and outputs, just like we did earlier when we were calculating average rate of change, can really help translate that into a sentence and get your units right. Okay, so let me give you, no, it's not your fault. I should stop.